All right, anybody have questions? No one's going to try to turn their projects in late, right? Okay, just checking. All right, so let's talk about second order noise shaping, and in particular let's review what for a discrete for a switch capacitor what first order noise shaping looked like. So let's write V out of Z. And what was that equal to? I'll start you off. Vn of Z anybody? Yeah, Z to the minus 1 plus VQE of Z times 1 minus Z to the minus 1. And why was it called first order noise shaping? Yeah, because the first order differentiation. So second order, what we're going to do is the following. Easy. V out of Z is equal to Vn of Z times Z to the minus 1 plus VQE of Z times 1 minus Z to the minus 1 squared. And so what happens when you do, so everybody sees why it's second order differentiation? Easy. What happens when you do second order noise shaping is you get a response which looks something like this. Now notice the second order noise shaping in the frequency of interest is flatter. Okay? However, the big problem or the issue with second order noise shaping is that at higher frequencies you get more signal, so it's not as easy. I mean, it's still fairly easy, but stability is more of a concern than what you have with first order noise shaping. Does everybody see that? And again, we're not reducing the quantization noise, rather we're pushing it to higher frequencies. So if I go right now, the quantization noise, which for now, well, let me ask a simpler question. So what is the noise transfer function for second order noise shaping? Well, it's 1 minus Z to the minus 1, right? And then plug in, yeah, the Euler's identity, but to get the formula, but I'm not going to rederive that again. And that's equal to VLSB squared over 12 Fs times 16 sine to the fourth of pi F over Fs. And refresh my memory. What was it for first order noise shaping? From the beginning of the chapter. It was 4 sine squared. All right. So if we then look at the VQE RMS, and you're going to tell me on this, what are the assumptions? So when I write this, I write, whoops, VLSB all over square root of 12 times pi squared over square root of 5 times 1 over k to the 5 halves. What was the assumption here? How did we derive this? Refresh my memory. What's that? No, how did we calculate the RMS quantization noise from the modulation noise? Well, we just right, we have the filter here, it does this, right? But we apply a square law, a filter with a bandwidth B, and then we integrate this from 0 to B to get the quantization noise, right? Does everybody follow that? Remember? All right, I'm going to ask you these questions on the final, and I don't want to be like, they don't know this, okay. Because it's B is equal to, what is it, Fs over 2K, right? All of the noise is what? No, the noise here. Wait, I'm assuming this is the noise, so I'm assuming this is this signal here, right? then I'm integrating this from 0 to b df, right? And then all of this stuff out here gets factored out. Yeah? Yeah, but it repeats, right? I mean, if you look at the spectrum, that's a sinusoid. It's going to go up. This spectrum's going to then repeat, right? So then when you pass the signal through the bandwidth here, all of the higher order stuff is removed because it's an analog signal. Yeah? Yay or nay? All right. Well, I mean, if you don't agree, say no, I don't understand. Yeah, if you go up. Yeah. No. Wait, if you don't want it. Yeah, but we can't integrate from here to the Nyquist frequency because then we get a huge amount of noise, right? Well, no, wait. Well, wait a sec. Before we leave, hold on just one sec. So then the next discussion after this was passing the output through a sync filter. And the sync filter's got a periodic response. This one doesn't. This one only goes 0 to B, and so all this other stuff is out. So what page were you talking about? 190? Okay. Yeah, because this is a Nyquist rate converter. It's not an oversampling or noise shaping converter. So with the noise shaping converter, if you go and you integrate all the way out to FS over 2, the noise is huge and it's not useful. All right, so, and then the next step, which I'm not going to go through, was passing the modulation noise through a sync filter. So what I'm going to do then is I'm going to take this VQE RMS and I'm going to calculate signal to noise ratio. And if I do that, then my SNR ideal, and again, this is assuming an ideal brick wall filter that ends at B, not a sync filter. But remember, it's pretty close, but the sync filter can attenuate the desired signal. Anyway, we get the following: 6.02 N plus 1.76 minus 12.9. And the reason you put it like this is just so you can see it in terms of the Nyquist rate converter, plus 50K, 50 log of K. And let me just make sure I'm recording. Paranoid. Okay, and so if you look at this, for every doubling in K, you get 15 dB improvement in SNR. Okay, so if I said your SNR went up by 6 dB, how many effective bits, or how many bits did it go up? Okay, one more time. 6 dB, how many bits did it go up by? 1, right? And so if I get 15 dB, it goes up by 2.5 bits. So for every doubling in the oversampling ratio, I get 2.5 bits increase in effective number of bits, right? So what was it for first order noise shaping? 1.5. So let's compare them. Now, I'm going to show you the plots of improvement and resolution. So we have simple oversampling, Now, practically, that's a problem because we can't put a DC signal in and get any improvement, right? Now, when we use a noise shaping modulator, we can put a DC signal in because it has feedback. So Bennett's criteria don't have to be valid. But if you look at this, if you go to, like 3264, you're really getting a significant improvement in performance, okay? So that's why if you can get your projects to work with second order noise shaping, I think that's pretty significant because you get a really good improvement for every doubling versus first order noise shaping. Now, I know that when you say something once, people don't get it, but where's an example that you can use to look at continuous time noise shaping? On CMOS EDU, where can you get a simulation example to look at for first order noise shaping? I'm sorry, where can you get a continuous time second order delta sigma noise shaping example using the K delta 1 sigma? Where can you download that? Yeah, well, is it in Errata or is it, yeah, I think it is Errata. Yeah, right here, right? This thing, okay? And now just to make sure, because we spent all this time on this, if I have a resistor, let's just say 1K, and I have two switches in series, the only time the output of the comparator is fed back to the input, to the integrator, is when both of these switches are closed. So if they're closed for T over 8, and I've got 8 paths, then each one of these resistors, all added up with all 8 paths, would correspond to a single path with one resistor of 1K. What I'm getting at now is how do I implement those two switches? Okay, so what I want to do is I want to do something like this. Now, you might be able to do your design where you don't need these, but if you haven't taken the digital class, so this would be, to turn this on would be clock bar. So I'm not going to insult anybody here, but I want to make sure you follow. So when you put your PMOS, you got to make sure that the body of the PMOS is connected to VDD and the body of the NMOS is connected to ground. The simple way to think of this is that when you put a 0 here, it turns the PMOS on. When there's a 1 there, it turns the PMOS off. Here, when you put a 1, it turns the NMOS on, and when you put a 0, it turns the NMOS off. That's why when we had our clock signals and we did our clock generator, it would be probably useful if you take out not only the true signal, but the complement signal so that you have one immediately available for clocking the TG. Does everybody follow that? And if you're not used to this, you can waste a lot of time if you don't have the body of the PMOS, and it's hard to look at with the symbols in LT Spice, at VDD and the body of the NMOS at ground. Okay, so there's a couple other issues, but before I do that, so this implements one of these switches. You put clock and the opposite complementary clock just like this. Now, why do you need both? And again, if you haven't taken a digital class, yeah, so NMOS passes 0 well, and the PMOS passes 1 well. See, the NMOS will pass when you put a 1 through it, it won't all the way go to 5 volts. So if you put them in parallel, you get a gate that passes both fine, all right? Okay, so one other big issue here. These devices have some resistance. So you say, okay, well, I've got my resistor coming in to the integrator, so here's VN, and it goes into my integrator. I'll just draw it like this, and then you have a feedback, and you put a resistor here, and then you put your switches, these TGs, in series, and it might work better to have them on this side. It might work better to have one on each side. I don't know which way to put it in. I think it doesn't matter, but this comes from the comparator. It comes down here. The problem here, the concern is when you turn the switch, these TGs on, they also have a resistance. Does everybody follow that? And if you don't set the sizes wide enough If you make them too wide, then they're a big capacitive load that you have to drive from your oscillator. So you got to make sure that they're turning on and off quick, because if they're turning on slowly, things won't work well. Okay? They have a resistance. So if I make these wide enough, let's say that I make, let's just guess, how about 24 microns by 0.6 for the PMOS and 12 microns by 0.6 for the NMOS. The reason I make the width W over L 2 times is because then they'll have the same resistance. Okay, PMOS is higher resistance than the NMOS. If I do that, then they're going to have less than a kilo ohm of resistance. The problem is, well, I only have a resistor with a kilo ohm. Okay, so I might even want to make them bigger. But what I'm going to do is I'm going to look at this side, and then I'm going to look at this side and see what the voltage drop across the switches are. Does everybody follow that? Okay, so now, let's say that I get this resistance and it gets down to 100 ohms. I still have a problem because this resistor here is 1K. I make this 1K, and unless I fiddle around, which isn't a good idea to do, I'm going to try to make this 900 so that they match. The problem with that is, with process and temperature and all that, they don't track each other. So how do I fix that? So this resistance and this resistance, okay, so before I answer that, does everybody get the idea that putting the TGs here and the finite drive coming out of your comparator, so you might have to put some inverters here. Remember, what did we do for the inverters in LT Spice in our oscillator? Yeah, we use stronger ones, right? You may need to do that just to make sure this goes close to 0 in VDD. You don't waste time on this. You simulate it and you look and you decide, is it fast and is it going to 0 into VDD? If it's not, then you know you need more strength here in your inverter, which means you need to use wider stages, and you might need to use a cascade, okay, just like we did. But then you say, make sure all your signals are fast. Now, how do I compensate for this resistance here? I'm going to use dummy TGs. So what I'm going to do is I'm going to take and put in series with here some TGs that are always on. So this one's at VDD, this one's at ground, and if I have two here, I'm going to do the same thing. You may decide, hey, I'm going to be able to do this with a TG that's on half the time. I don't think that'll work, but who knows, maybe it will. So these are always on in your input, and then I go to my resistor. And then there's my input. And now this resistance will track this resistance minus whatever the drive is of your output comparator. Does everybody see the issue? Okay, so let me just comment on this a little bit further. But does everybody understand? Okay, so if you don't do this, you're going to get a gain error. Okay, so just be aware of that. Does everybody understand? I got 1K, TG, TG, and then whatever the resistance is of the transistors here driving the output in the inverter. Now, you have to be careful, because if you put too much delay here, your design will not perform well because you got too much feedback delay. Yes? How do we implement these? Yeah, it's just exactly the same. The only difference is here you physically tie the gates to ground. Yeah, so they're always on. Okay, so now here's the issue. You could argue, well, wait a sec. Why do I even need this 1K? I got these transistors here already. Why do I need to add the 1K? Why can't I just use two TGs here and here? The problem is, and you might get it to work somewhat. What's that? Yes, that's exactly the problem. The resistance of the TGs isn't constant. It's going to vary a little bit with the voltage that is applied across them. It's not going to be a linear resistor. So what I'd like that to dominate. This resistor to dominate, to be the one that determines the overall resistance. Well, you could do that by making these really wide. Well, if you make them really wide, they have low resistance, but now the problem is you have to drive those gates, which then if you make them wide, they're big loads. So then your clock generator has to be beefed up so that you get nice fast transitions here. Does everybody follow that? Because if I'm turning these on for 1 nanosecond, I need to have edges that are like 100 picoseconds, or else it's going to do something like this, you know, and it's not going to be a well-defined feedback signal. Any questions? Okay, one last thing. Yep. Um, integrator. But if you, so you're feeding back signals here that turn these on for a finite period of time, like 1/8 of a. Yeah. Right. Um, and you're feeding back a big enough signal through here. All right, well, look at the charge. So plot the current through here just to make sure you're getting the right amount of charge. And you're using like a self-biased diff amp. Well, try replacing the self-biased diff amp with an ideal amp and see what happens, because it should work. I mean, it's not really that much different than the switch capacitor, because with the switch capacitor, you're chunking back charge for a period, right? Now, if you haven't controlled these well and you're not looking at the clock signals and they're not turning on abruptly, so, I mean, because you can't tell what they're doing. Well, but again, keep in mind that to turn these on and off very quickly, I mean, that's going to have some delay. You may not be able to. Yeah, so you need to look at the charge that goes through here, because if you're not getting enough charge through, it's not on enough. You may find out, hey, I need to keep these on for 1/4, and then I get a gain difference, but that's fine. No, you can still do 8, but remember, because remember, if you turn them on for a finite period, let's say ideally you're doing this, right? Okay, so let's say this is 1/8. However, because you have finite clock signals, say that's 1 nanosecond. You have finite clock signals, instead you get something like this. And then this is from here to here, or maybe you could draw it as t/4, t/6 if you adjust the clock phases, right? Well, this amount of charge that flows, and you have to look through here, is the same as what you get in this. And so it ends up being equivalent to clocking with the faster clocks, but because you can't turn the devices on in 1 picosecond, you get this slower turn on. No, that's fine. Yeah, I think ideally you don't, because it'll make mistakes. But it's not going. That's the whole point. It's not going to be ideal. You're going to feed the signals back. There's going to be some. I mean, unless there's zero delay. Yeah, you'll lose resolution. No. I mean, it'll, depending on how slow the feedback path is and how well you control these, the resolution will drop. Yeah. But no, it's just the exact same thing as your water level in the buckets, right at the common mode level, right at the level. It's going to do that. It's going to go 1 0 1 0 1 0 1 0. But overall, you're not going to get a net increase or decrease in the water level. It's, you know, you could argue, oh, you made a mistake and it's still a little high, but it averages out. So ideally, you don't want to have this. You want to turn them on. But if you have the signals here and you look at the charge or the current that flows through the resistor, and you see that it's a small amount of charge, then you know you have to adjust the clock so they can turn on and put back a more reasonable amount. Because everything has got delays in the feedback and turning these on. Remember, there's a process characteristic time constant that says I can't turn this device on any faster than this. whatever it is, and it might be 100 picoseconds in this process, so you're dealing with that. But how much did you look at the current through the resistor? Look at the current through the resistor, because it may be that your gates are turning on, and you're looking at, oh, the gates turn on nice and fast, but you don't know how fast the actual transistors turn on, and you start getting current flowing through them. What's that? Yeah, make sure, yeah, get it to work slow and then speed it up and look. But if the problem is, if it works slow, then this T over 8 is going to be more and more ideal, right? And so it'll work, and then when you go fast, it'll stop working, and then you'll need to readjust the clock phases. Yeah. 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 So you say, okay, I'm going to clock. So here's the issue. I'm going to clock this with, say, phi 1. Okay. Then I'm going to say, I'm designing this comparator so I guarantee that after 2 phases of the clock at phi 3, the output of the comparator has made a decision. Now I want that to be as fast or as close as possible to phi 1, because then I minimize the delay. And delay in the feedback path is bad, okay? So, but I say, okay, by phi 3, it makes a decision. Now you got to verify that, because if it doesn't occasionally, your signal to noise ratio is going to be crap, okay? So then you say, okay, then I'm going to, at phi 3, I'm going to turn these on, and you might use phi 6 here, so this is already on. And then you say, okay, then at phi 8, it shuts off, and then you get your TGs turning on. You have to close. Ideally, you want to do it immediately after you clock the comparator, but again, you have the delay, so you have to close these when you know the comparator has made a decision. No, it's going to vary, because if you overdrive the inputs, it's going to switch faster than if they're real close together. Then it shoots out the delay, and that's going to set your feedback time. And the problem is, it's always going to drive the inputs of the comparator. That's the whole point of the feedback loop, drive them together. Yeah, but you don't want to do that. You want to pick what it works for the fast and the slow. The problem is, if you do that, your slow isn't going to give you as good a performance, right? Because you're being over conservative in selecting your clock phases, right? Yeah, you can't change things, so you have to do it for the worst case. It's not optimized. I mean, unless you can slow things down, there's going to be trade-offs. So you're going to say, well, if I do this, it works better, but if I do this and slow things down, it works better if I do this. It's not going to be, this is the answer, woohoo. You know what I'm saying? All right. Uh, that's good. Well, no. If you adjust the clock phases so that it works well at high speed, if you can somehow make the clock phases even closer together so that at lower speeds, then your signal to noise ratio will go up even further. So if you say get 8 bits at high speed, which was good, then you say, okay, well, if I slow down the clock, I still get 8 bits. Well, but if I slow down the clock, but I use earlier clocks, so I don't use, phi 1, I don't use phi 3 or whatever I said in these examples, I use phi 2, then you have less delay and the SNR will go up. Does that make sense? So you try to do it for high speed so that it will work fine, with the problems of comparator delay. So you're conservative when you select these after here. But if you go slower, then that comparator delay may not be an issue, and you can make these a little tighter and closer here, and then your SNR would go up. Yay? Nay? If you put ideal stuff in, everything's good, because you can make the clocks like the example I put on the web. it's immediately, you clock this and then you immediately clock these. No delay. That's maximum SNR. Then you can slow down and the SNR is going to be the same, right? But if you have a real comparator, you can't do that because the comparator has some finite time to make a decision. So you have to clock these a little later so you make sure the output is fixed. So yeah, then you have to increase the integrator capacitor so you don't saturate on your output. But I mean, I'm not saying real slow. I mean, just slower, yeah. You don't want the capacitor to be too big because then, well, yeah, then you get less swing here. So that, I don't know why you're not getting swing, but it's easy to see if you're not getting swing. So it goes, this node's going high, low, because that means it's unstable. Yeah, you can troubleshoot it, because if this goes up, it should slam those comparators to make the decision to feed back the signal. Now, if it's feeding back such a weak amount of signal, then that's likely causing it to be unstable. So you need to make sure you're getting enough signal fed back. Yeah. All right, so hopefully the projects will be well. What I'm going to plan on doing is not this weekend, but next weekend, being available in lab, the TBEA 311, so that if you have questions, I'm going to do that for the other class too. I can answer, we can look at things. Okay. If you're waiting till the weekend after Thanksgiving and the projects are due, I probably won't come in then because it's too late. All right, let's because you can, when you start messing with all this stuff, you can waste a lot of time on simulations and stuff. Why didn't that line show up? All right, so what I'm going to do here, or actually, you know what? Let's do it this way. What I want to do is I want to remind you for the second order noise shaping, we covered that just a moment ago. But if you recall, for this feedback loop, the V out of Z was equal to 1. We derived this at the end of chapter 5, I think it was A of Z divided by 1 plus A of Z times B of Z times Vn of Z. And then that's plus VQE of Z times 1 over 1 plus A of Z, B of Z. Does everybody recall that? And refresh my memory from half hour ago or so, what did this whole term equal? Z to the minus 1. What's that? Well, hold on, because remember that we're going to have 2 integrators, and that's 2 feedback paths, and here I'm only showing 1 feedback path. And then the other term was this term right here, and remind me, what was that equal to for a second order modulator? Oops. All right, so let's quickly, well, actually, I'm not going to spend the time on it. I'll just show you on page, because it's derived there, on the bottom of page 254. You see A of Z is then equal to Z to the minus 1 divided by 1 minus Z to the minus 1. So A of Z is the forward path. That's a delaying integrator and a non-delaying integrator. And then on the feedback path is 2 minus Z to the minus 1. So if I look now here, this A of Z here is then Z to the minus 1 over 1 minus Z to the minus 1 squared. Does everybody agree with that? What we just wrote? That's a non-delaying integrator and a delaying integrator. And what was another name for this that I used on the previous slide? A of Z. All right, and then B of Z was equal to 2 minus Z to the minus 1. And so here I have my output. So this terminal is V out plus V out times 1 minus Z to the minus 1. Passing this through here. Does everybody agree that gives me at this terminal the transfer function of 2 minus Z to the minus 1? Everybody agrees with that? Angshman? Well, wait. Here's the output. The output is added to the output times 1 minus Z to the minus 1. I sum those together, and we'll call this whatever, V fed back. And so V fed back is equal to V out times 2 minus Z to the minus 1. And B of Z is equal to V fed back over V out, which is equal to 2 minus Z to the minus 1. Everybody agree with that? Anlan? All right. So then what I'm going to do, I'm going to split these up, and I'm going to push this through here so that I'm going to move, I'm going to have two paths. So I'm going to keep this path here, which is this path. And then, why didn't that show up, I wonder? What I'm going to do is I'm going to push this through to here so that I can connect this output here, but I can only do that if I push the integration into there. Does everybody see that? And so then I've got 1 minus Z to the minus 1 divided by 1 minus Z to the minus 1, which gives 1. And then here I've got V out still coming back, and so there's my delaying integrator. There's my non-delaying. Looking good? Okay, so this is my topology for second order, noise shaping. And I'll show you implementation in a moment. But basically, the output's fed back to the input of a delaying integrator and back to the input of a non-delaying integrator. Any questions? Okay, so I'm going to tell you this, when we implement this, it's really, you can't implement a non-delaying integrator in switch capacitor. So let me just comment on that real quick. So if we go back to chapter 2, and I look at that table we had in chapter 2 here, and you say, oh, okay, well, let's say that I connect my output, I have my input, say V in minus my fed back signal, but my input is delayed, and I'm going to use, in my second stage, my delaying integrator, I'm going to connect the output of my first stage through a Phi2 switch to the delaying integrator. Would everybody agree that if I just thought to myself, because this little delay of the input is just a half clock cycle, really, when I implement this, when I implement the second order modulator, what I get, instead of the input coming in at 0, the input comes in a little bit later. But it doesn't influence the implementation. It just means my input comes a little bit later. So the true transfer function would be, for the second order, would be Z to the minus 3/2 instead of Z to the minus 1. It just means, hey, my input's coming a little bit later. Doesn't influence anything else in the circuit. Did I lose anybody on that? Okay, so when I go back and I look at the transfer function here, where is it? Instead of the input coming in at z to the minus 1 and going, it's z to the minus 1/2 because it effectively arrives a little bit later. But everything else is exactly the same. Did I lose anybody there? Okay, I'm assuming it's a real simple concept. It just means the input arrives a little bit later because I can't implement a transfer function with of a switch capacitor with no delay in either of the input signals. Okay, well, as long as I have them clocked on opposite phases. All right, so I want to briefly talk about the gains, and this is figure 727. So what I'm going to do here is I'm going to throw some gains together. So I'm going to add a GI here for the gain of the integrator. So just tell me, what is the GI in like a simple switch capacitor? Yeah, CI over CF. So I'm just writing it as there's GI, there's 1 over GI, so it's exactly the same. Then I push that through to the next stage, and when I push it through from here to here, I have to also push in a G here so that the overall effect of the feedback signal is 1, G sub I, so this is what I have. But what am I not showing here? Now, I'm not showing the gain of the comparator, GC, right? Here, this is exactly what I was talking about a moment ago. Really, I just am delaying my input signal, but it doesn't influence any of this stuff over here. It's not in the loop. It comes in a little bit delayed, but it doesn't influence any of the loop dynamics or anything that's happening here. Okay. Now I write these two signals here. I don't show the G, but what I want to do is I want to take and say there's a gain associated with the non-delaying integrator and a gain associated with the delaying integrator, and look at the stability and make some comments. Now before I do that, let's look at the implementation, the switch capacitor implementation. And here we have our non-delaying integrator, which we know, hey, it actually delays the input by half a clock cycle. Here we have our delaying integrator. We have our gains, G1, CI1 over CF1, G2, CI2 over CF2. And our output is our digital 1 and 0 that goes through, and we decimate and all that. So what we want to do is we want to look at the gains. And before I do that, I'm going to do a simulation. So let's go back here to the old lecture notes. Today's 11/14/14. And we go here. And let's look at figure 729. So what I've got is I've got a gain just, okay, so I'm using the same gain as I used in the first order modulator, 0.4. So I got 0.4 and 0.4. What I care about is what's the output swing here and the output swing here. And I'm using a power supply voltage of 1 volt, and so I want the outputs to swing within 1 volt. And I see they don't. And the problem there is then I get integrator saturation, and that's not good. Okay, so what I'm going to do is I'm going to adjust these capacitors. But I want to kind of have an idea for how to adjust the capacitors so that I get the best performance. Now I could fiddle around, but I'm not going to do that. What I'm going to do instead is I'm going to try to determine the gain of the comparator. Now let me refresh your memory. The gain of the comparator is the 0 to VDD on the output, 1 volt in this case, divided by the swing here. But the swing here is going to be varying, right? Sometimes it'll be little, sometimes it'll be big. So how do I determine the average output and the average input of the comparator? I'm going to put RC filters on there and look at it to determine what the average is. And so if I go look at figure 38, I have the exact same circuit, except it's a little bit different. I'll comment on that in a moment. Except I've added these filters to try to determine the average. And if I determine the average, then I can get an estimate for what the comparator gain is. So let's see what we got. So V out, let me see where it is. V out 2 is the output of the comparator, and V out 1 is the input. So V out 2 is 0.1, V out 1 is about 0.4, we'll say. So I get a gain of the comparator about 0.25. And let me also comment that when you're looking at stability of modulators, which I'm going to talk a little bit more about in a moment, this technique of looking at the average is really useful because it gives you an idea for what value that we talked about when we did our gain calculations. What was the variable name? What do we represent the gain of the comparator as? GC. Remember when we put the GC in, we had a GC where we placed this in series with the input of the comparator or output of the comparator. So we did the following. We said, oh, here's the comparator. It's a noisy block, so we got this VQE of Z. It's coming in here with our adder, and here's the output. And then what we're going to put in here is a block called GC that represents comparator gain. Does anybody remember that? One person? Are you sure you remember? All right, I believe you. All right, so let's go talk more about the equations for finding the gain. But before I do that, let me point you to some block diagrams. Are there any questions? Does this seem unreasonable? What's that? But wait. So the only time, remember this signal here is swinging, right? And if we make this capacitor smaller, then the signal is going to get bigger. Yeah, so, ideally, if it's an ideal comparator, you could get 1 microvolt here, and the output would change. So, yeah, infinite gain, right? But in reality, when you're doing the system level block diagrams, you have some swing here on average, and then you have some swing here. And so the swing, or the gain in that sense, with an ideal comparator is then finite, and we just calculate 0.25. Having said that, does that mean GC is 0.25? No, because from one clock cycle to the next, the gain is going to change. And so there's situations where we're taking a complicated signal here and we're trying to dumb it down to a simple little, oh, the gain's 0.25, so we can get some idea on how to select the capacitors. But it does not mean that the system's going to stay stable, because it's changing. It's a digital system. It's changing from one clock cycle to the next. Yeah, you're trying to characterize the gain of the comparator so you can select these capacitors to maximize the swing, because ideally you want this swing to be as big as possible, because then you have large forward loop gain, right? And then you can resolve smaller signals, right? Yeah, trying to figure out how to select those but let me ask this. If I make this capacitor small, does it make the gain of the integrator big or small? If I make the capacitor small, does it make the gain of the integrator big or small? Small. The gain is, yeah, it's 1 over RC for the integrator, right? So this would be, if I look at this as a switch capacitor, oops, bigger. Yeah, so then the gain of this stage would be 1 over RSC times C. So if I make C small, I get a big gain, meaning I get a big signal there. So I want C to be small, and I also want C to be small because then it doesn't have as big a load here for the integrator to drive, so it'll be faster. Yeah, but if it's too small, then you saturate and your bucket overfills and you lose your information and your conversion's bad. That's why this is important. So how to select these things. All right. So if I look now at let's just put, I'm going to make this a little bit generic. And okay, so let's pause right here and look at this block diagram. So, oops. This represents the gain of the discrete analog integrator. So this is CI1 over CF1 is G1. This represents G2 is CI2 over CF2. I could put gains in both feedback paths, but I'm saying I'm only going to adjust the gain here and it'll be less than 1 of this feedback path. Why is this feedback path more important than this feedback path here? Why did I pick a gain here? Yeah, because it's closer to the output, right? So if I feed this back, if I go through here, I feed all of the output back here, my integrator's rolling off. It goes through 2 of them, but here it's closer to the output, so it's going to be stronger and better able to influence the output. So my critical feedback path is right here. Does everybody follow that? Simple example, if I have a speaker and I'm worried about instability, the further I take, a microphone, and the further I take that microphone away from the speaker, the more likely it'll be stable and I won't have positive feedback and hear the screeching, right? Same thing here. The further I take my signal away from the output, the less likely I'm going to be unstable. This is the critical path. This is the one I need to focus on. Any questions about that? It's just saying, okay, I could put something here, but I'm not going to because it doesn't give me any more improvement. All right, so let's look at the derivation. If we go through, and it's in the book, and you look at the equation, and you ask, oh, one other key point. Notice I'm defining GF as G1 times G2 times GC. Okay, so I go back and I derive the transfer function. And here's the transfer function. So if I have ideal situation, GF is 1. So normal operation, GF is 1, and tell me what the equation reduces to. So this goes away, and then I just get z to the minus 1 times Vn. Exactly my ideal situation, and my feedback loop's going to try to drive GF to 1. And then if I look here, I get the bottom goes away, except for the 1, and I just get second order differentiation. And so then I ask, all right, where are the poles located? Does everybody follow that? So my forward gain is going to go to 1, and then it's going to operate properly. Where are the poles located? What's that? No, well, yeah, ideally they're at the origin, so you just get delay. But if the forward gain's not 1, because remember, I'm taking a nonlinear system that's bouncing all around, and I'm saying, oh, it's linear. And I'm treating it, oh, this is GF, it's a number. Well, it's not really the way it is, right? It's varying. So I'm taking a complex, chaotic system and trying to say, oh, this is what's happening. So if my forward gain stays between 0 and GF of 1.33, then I'm stable. If it goes above this 1.33 or below 0, then I become unstable. So going below would mean I'd have positive feedback. So what was it for the first order modulator? Does anybody remember? What was this equivalent equation? 2. the maximum was 2, so the stability was easier for the first order modulator, and intuitively you're simply repeating, oh, well, the modulation noise is higher at high frequency, so yes, it's going to be more prone for instability. All right, so then the question is, well, how do I select the G1, the G2, and all that? And I have some discussion in here. I'm going to go over it very briefly, and that is if I set that all of these equal to 1, then I get the proper behavior and I get these poles. Note that what I want to do is I want to have some control over how I implement things. And so what I'm going to do to implement the G3 is I'm going to add this other path here. So this other path for my G3 would then have a gain of CI3 over CF2. Okay, and then G3 is, yeah, because it's coming back this way through this switch. So it's given here CI3 over CI2. And then I can make some estimates for how to set that feedback signal. So let's look at that in the simulations and see what we have. Okay, so let's look at, close this, and look at 36. And let's look at what happens when I implement this. But before I do that, how would I set G3 equal to 1? GI3 to 1. How would I modify this circuit? Well, we'll come back to that. Let's just look at the sim. And there you say, now look at this and tell me where you're worried about instability. Yeah, this is starting to go woo, which looks a little non-linear, so it starts to becoming. If I want to, tell me a couple ways I could make this modulator more stable based upon what we've discussed. Okay, so if I make G3 smaller, but let's do even simpler. How would I make it stable if I didn't change anything in here? Yeah, reduce the input amplitude, right? So if I went to, oh, I'm going to go to 0.25 and hit run. Nice and stable, right? Now if I go back, though, and put it at 4.5, and then I see, oh, there's my instability. Now I want to make G3 smaller. So if I go back and I look, G3, was CI3 over CI2. So I can make CI3 smaller. Okay, so that will, well, wait, we have to be careful here, because CI3 smaller will reduce the output swing of the integrator, but it will also reduce the GF, and so one of the other gains will have to go up, which will have to be GC. So let's go put this, let's try just 0.1 and hit run. And so I expect my output swing to get smaller, but you still see this funky looking thing, which is kind of questionable for stability. Okay, how would I, so the key takeaway from all of this is for second order modulator, and if you're doing your projects, it's harder to make it stable. Okay, so that's the key takeaway. Now let's answer the question, how do I make G3 equal to 1? Tell me what to do. What's that? Well, yeah, I could make this so that it's 0.4. That would work. But let's make it so that it's real simple. Let's just do the following. I know what you're all thinking. You got a floating node there. Whoops. Oh, that's right. Come down here. Tell me what to do to finish, to set the gain equal to G3 equal to 1. Yeah, I just connect this up, right? Right here. Boom. Does everybody agree with that? Does anybody agree with that? All right. So then let's see what happens. Still see a little bit loopy, but it's a little bit better with regard to the output swing. Still a little bit out. All right. Are there any questions on, well, on the second order modulator? Yeah. Well, but wait a sec. Um, we, no, I know, but remember, just to be precise, that before you shape the noise, you have a spectrum that looks like this, right? So after you shape the noise, this area has to stay the same. You get something that looks like this, where the noise is the same, right? So it's not that we're not, I mean, before we do the noise shaping, and it's all the same up to f sub s over 2. Yep. So with second order, it's the same thing, except you get something like this, and then it goes up higher, but the area is right here. No, it's not the same. It's, if you look, let's look at, well, at DC, it'll be the same, because at DC, there's zero noise, right? However, if I look at lower frequencies, if I look at this and just plot them, and I look, what's that? Well, if you look at even, I mean, if you look at the log of these, it's only exactly the same in 0 at DC, but as it starts to move away from DC, you still get less noise for the second order versus the first. Um, well, here, no. Let's, just to make sure we're clear, let's go back and, where is this? So where's our .tran? Let's start at 1K, all right? And then hit run. Looks exactly the same, right? And then here, I'm going to put logarithmic, okay. And then here, I'm going to limit it to, what'd you say, 2 meg? And you look, and that even if you go down almost to 0, the second order noise shaping is still going to be lower noise. It's only when they both get to DC that it's exactly the same, which is 0. So, does everybody follow that? Now, one thing that you have to keep in mind that comes into play is that when you do a DC sense, it's not like it's DC, right? It's actually like it's like windowing. It's a finite set of time where you basically are applying a DC signal, looking at it for a while, and then shutting it off. Okay, so that's, I think it's the same for second order and first order noise shaping in my mind, but when I think of it that way, I go, well, I got a pulse here. Well, wouldn't the second order noise shaping work better because it's actually a transient? So what I'm saying is, if you look at like sensing like this, where it comes up and it goes, okay, well, I'm going to start sensing right here. So you could think of, okay, I have 0 input on my sensing, and it comes up and it goes over and then goes, and this is the top time when you're, Well, this corresponds to, in the time domain, of sensing like a pulse, right? Like a sync function. And so in my mind, I think that if you're using second order noise shaping, this could work better. However, if before you say I'm starting, you let your sensing circuit run, then I think it'll behave like a DC circuit, and you won't see any difference between first order and second order. Did that make any sense whatsoever? So if I have a DC signal, and if you just talked into the computer screen and said no, I probably heard you. All right, so I got a DC signal and I got a sense circuit here, sense amp, let's say, right? If I close this, then my signal here looks like this, right? So it's not DC, it's got a transient. So in my mind, there may be a benefit to using second order versus first order. You can play around with this and see for DC signals if there is. However, if this is always closed and it's running, so you get your 1010 out and you enable and disable the sense amp, I don't think there is a difference. Does that make sense? Little? Okay, something to think about. Okay, so real quick, I want to cover just briefly using two delaying integrators, and I'm just going to make comments about that. When you use two delaying integrators, like as seen here, if you have a large oversampling ratio, you won't get instability. However, you start reducing your oversampling ratio, you will get instability. And the benefit of using these is that you can get more time for the comparator to switch states, but generally there's no deep thought here. If you have more delay in your forward path, it's going to be more unstable, right? I mean, it's like me saying I'm going to drive my car, but instead of looking at the road, which is the forward path, I'm going to look at the road after a 1 second delay. Well, if it's a 2 second, 3 second, the more delay I have in looking at the road, the more unstable I'm going to be driving my car, right? It's the same thing. If I had more delay in my forward path, then I'm going to have more chance for instability. So don't think of the math, all right? And then last, but does that make sense to everybody? More delay, more likely unstable. Yay? No one's saying anything. Friday after. Well, don't think deep here. What? It just says that if I add forward delay in the forward path or in the feedback path, then controlling things is more challenging and it's more likely to be unstable. Like if forward delay would be like a delaying me seeing the road as I'm driving. Feedback delay would be delaying me hitting the brake, and before the brakes actually apply, there's a delay, right? It's more likely there's going to be problems. All right, and then finally, selecting the modulator gains. Here I go through and select and put a discussion in how you adjust the gains for G1, G2, and G3. And you can see this, oh, this is the answer, and this is what I'm going to do. Rather, there's a trade-off here of what you can do. But you ideally, so let me ask, let's actually look at this and just make sure everybody's on board with this. If you look at this topology and you say, okay, well, if I look at what it says here, G1 is 0.2, G2 is 0.4, G1 is 3. I run the simulation, I look at the outputs of the integrators, they look good. But you ask, well, I'm above the supply range here, and why don't I just increase these gains? Like, why don't I just put this at, well, no, what am I saying? I want to reduce these. Why don't I just put this at like 0.1, etc., and rerun so I get a smaller output signal, and then of course my output here goes lower, so I gotta, I'm missing the point. What's the point of, what are we trying to do here with the outputs of the integrator and all this stuff with all the equations? What's the whole point? Yeah, we want to get as big a swing out as possible without saturating. We want those signals to swing big because then we have more forward gain and it's easier for us to control things. We could just design this so we get little teeny tiny signals here, never have to worry about the integrator saturating, but that's not what we want because then the comparator has to be ideal or has to work better. We don't want that. We want it to be very decisive that, hey, I need to remove a cup of water here, and you only get that when you get big swings here. So keep that in mind. And you get big swings by using small capacitors, which also pushes out the bandwidth of your integrator and makes it easier to drive. Does everybody follow that? All right. Are there any other questions before we call it a day? All right. Have a good weekend. We'll see you on Wednesday.